All right, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 360 Control System class. Today is our 19th lecture, and here is the Gantt chart showing we're at this very cell. Well, of course, can you guys hear me?
Yeah.
All right. Okay. Definitely, you can also see my screen. I'm pretty sure about that. All right. So we are here, and it's supposed to be the very first lecture for the design via the Root Locus, but we need to finish 1.5 more examples for hand sketching the Root Locus. Okay, so let's continue this example here. This is the first example, and let me make better here. So the system block diagram is given like this, and we can see from given here, we can tell the first open loop transfer function, okay, KGH. And remember to use the open loop transfer function to plot the Root Locus for both MATLAB program and hand sketching like this, okay, for both. And remember, always use open loop transfer function. Okay, so transfer function here, of course, you are introducing the K gain here in the numerator, from which we can tell who are the open loop poles and who are the open loop zeros, because they are respectively what? Starting point and ending point. Okay. We have 3 and 3 versus 3. Okay, the numbers must be same. That makes perfect sense. And then we start at the Root Locus on the real axis, along the horizontal real axis. We place the 0, 91, and 92, 3 open loop poles. There's no open loop zeros. There's no finite open loop zeros, so nothing on the paper. And then we count from right towards left, right? Okay. And the Root Locus exists to the left of odd number of open loop poles and zeros. Those are counted, okay? In this particular example, we don't have open loop zeros there. That's why we are not counting on any. However, if any, we count them. Okay, we count them. We are counting the number rather than the values. Okay. From right to left, we come across 0, and then left to it is obviously we have 1 poles here. So 1 is odd number. So we do have Root Locus here. Keep moving, we come across second open loop poles, and so second 2 is even number. So left to it, there's nothing here. Keep moving to the left, we come across the third one, the third open loop pole. Then left to it, of course, we do have Root Locus. So this is the resulted Root Locus along the real axis. And then we take a look at the real axis Root Locus. We find this branch. This is single branch, individual branch. The starting point of 92 open loop pole. Ending point, infinity. Okay. Infinity is open loop 0. Consider here. So this branch is fine. However, this branch, what do we find? At 2 ends, we are seeing 2 open loop poles, which are the starting points. Both are starting points. So the Root Locus are moving facing to each other. Okay, facing to each other. And when they intersect at certain points along this Root Locus, they're gonna leave away the real axis, right? That's why we need what? Breakaway point. That's why we need breakaway point. It's not break in, but break away. Breakaway point. So we ended by here. So next is how to find this breakaway point. First breakaway point is obviously between -1 and then 0 as a real number. Does this make sense? Okay. And this must be very clear. Okay, your breakaway point is along this part of this section of the Root Locus, along it somewhere between 1 and 0, and it is a real number because it is along the real axis. This real number between 91 and 0, and leaving it So where is this point? How to find this point? Here's the formula. Oh, here's the formula. Here's the formula. Of course, before this breakaway point, we had the asymptote, which is not part of the Root Locus, but asymptote. We will see how to use them. You can imagine after we find out the breakaway point, the Root Locus can leaving that point, gradually approaching to the asymptote we found previously, right? This logic makes sense. This is what you can imagine. You can easily imagine, not something very difficult. So let's see this formula. What does this formula mean, basically? It means, so if we try to, well, of course, first we look at these open loop poles and open loop zeros one more time. 0, negative 1, negative 2, and 3, infinity. Okay. And how to write this equation, right? Summation. First summation is actually 3 reciprocal sum equals to another 3 reciprocal sum. Does it make sense? This is how you interpret this given formula, which means the m at the letter m in this particular example is equals to 3, right? 3 terms. Read here carefully. So listen up, everybody. The Zi and Pi are not the open loop poles and open loop zeros. They're respectively of what? Negative open loop zeros and negative open loop poles. Be very careful here. Once again, the Zi's and Pi's are not open loop zeros and open loop poles. They are negative open loop zeros and negative open loop poles. Okay, remain as delta plus something, right? Plus something, plus something. So the left-hand side of the equation is delta plus the negative open loop zeros, which is what? Negative infinity, right? Second one remains negative infinity, negative infinity. It's okay, it's infinity, but it's okay. The other end of the equation is what? Delta plus negative open loop poles, right? Open loop poles is 0, negative 1, and negative 2. But here is negative, right? So negative 0, negative 1 is positive 1. Negative negative 2 is positive 2. Does it make sense? This is how we write this equation. And further, it equals to what? Basically, the denominator here is the infinity, well, negative infinity. Negative infinity. Negative infinity. And here is delta itself, reciprocal, plus delta plus 1 reciprocal, plus delta plus 2 reciprocal, right? Take a look to see any questions you have. If this is fine, then how are we going to solve this? Well, let's try this out. I mean, this even. Of course, the left-hand side here, this summation of these 3 equals what? 0. That's right. It's nothing but 0. So 0 equals to 1 over delta plus 1 over delta plus 1 plus 1 over delta plus 2. So hopefully it is pronounced as delta. Is it? Anyone knows? better pronunciation? Another Greek letter? Anyone knows? Is it delta? Let's speak, please. I'm asking pronunciation. I doubt you're able to answer me by typing. Looks like a sigma, lowercase. Sigma, okay. Jesus. Sigma, okay, sigma. I will try to take a Greek 341 class, maybe, if it is available in this institution. I will try to make this up. Anyways, zeros equals to sigma reciprocal plus 1 reciprocal plus sigma plus 2 reciprocal. And how to solve this? I can give you guys 1 minute to try to solve this equation. See what you got. Go ahead. If you can use your calculator, just use it and let me know the answer. Let's see. Go ahead. What is the sigma value? Here, Sawyer got a sigma equals to 1. Obviously is wrong, right? I mean, you substitute sigma by 1. What do you got? Right hand, you substitute sigma by 1, then left hand side won't be equal 0, right? It's very easy to check, okay? You can check your answer easily because it's a very simple equation. I just want to make sure you are able to do this algebra. Anyone got any other answer? Anyone? Positive negative square root of 3 plus 3 divided by 3, which is equal to what? Same.
I missed a negative. It should be negative root 3 plus 3 over 3 or root 3 minus 3.
What is it?
I got like a negative 1.57 and negative 0.0422.
Yep, yeah, 2 got the correct answer. 2 got a correct answer. Okay. If it's good, working, then it's working. Because in the exam, you obviously cannot give me like an answer as square root of 3 plus 3 divided by 3. Well, but anyways, how to conduct this by hand? But this is something you need to do this, right? Plus delta plus 1 equals to 0. So the conclusion is numerator is 0. Okay. The denominator is a product among 3 sigma polynomial, but numerator going to be 0. From which you can tell is what quadratic equation of sigma. Therefore, your sigma gonna equal equals to 2 values. This quadratic equation is very easy to solve, and the result is negative 1.58, actually. A little bit off from 2. Such running is acceptable. That's fine. And then the next is, which is the one we should use and why? Anyone out there? Yep. Here. Kevin said this one is the right one. And why is that? It is between 91 and 0. Because going back to here, remember what we emphasized? This breakaway point is a real number first. Second, it must be between 91 and 0 along this real axis. Okay, so we are selecting this one. We are selecting this one. Okay, that's why. So abandon this guy. So now we got the breakaway point. We located somewhere here. Okay, it's located somewhere here. It's a little bit right to the middle point between 91 and 0, right? A little bit right to it. So it's about here. It's about here. You can label a little bit negative 0.43. You know, this is the breakaway point. And then the rest of the thing is very straightforward. What you need to do is just plot a curve, trying to gradually approaching to the asymptote. Breakaway point. Start leave the real axis. This way. And approaching to the asymptote. That's what the definition of the asymptote is. And always remember the root locus is what? Symmetrical about the real axis, right? Symmetrical about the real axis. So below the real axis, you have exactly the same thing. Okay. So in dark black color, hopefully you can see it, is the root locus. Okay. Asymptote in red, hopefully you can see it well too. Because under the dog cam, probably it's not very easy to differentiate color. So it's not too bad. Blue color is actually the axis. Okay. So this is the resulted root locus for this given system. And that's it. Of course, if you go to the handout here, we have section 2. However, section 2 is for the case where you have open loop complex poles and open loop complex zeros. Okay, we don't. Okay, I'm not planning to give any in the exam either. So, but if you're interested in, you can try this. Okay, a little bit complicated, but it's doable. Okay, we don't have any in the example 1 here, so we can ignore the section 2. We can ignore the section 2. But once again, it's all up to the open loop transfer function poles and zeros. Okay, it's starting with those. We're starting with those, just like we did here. Just like we did here. Find open loop poles and open loop zeros. And determine the numbers of them. Okay, how many of them? Okay, because this number is useful for you to find what? Remember, asymptote. Denominator here is a number, remember? Asymptote. Here, these two equations. To find asymptote, you need the number of open loop finite poles and the number of open loop finite zeros. Any questions regarding this example 1. So not example 1, literally it's example 4 for this module. Any questions? Everything's fine? All right, if it's fine, then let's do example 5. Once again, the system block diagram is given. Now, how to plot this transfer function, or say this system? How to plot this system Root Locus? So first of all, we still need to find open loop transfer function, right? It's very straightforward. As this, because of the unity feedback. And here we can tell the open loop zeros and open loop O's. What open loop zeros this time? And who are open loop O's? And how many for each one of them?
Zeros are -3 and poles are
-3.
poles are -2, -7, and -10.
Poles are -2, -7, and -10. Close, but not perfectly right yet. What we are missing?
Are all the zeros -3?
Are all the zeros -3? Nope.
Why wouldn't they be infinity like the last?
Exactly. Here we go. So basically, combining these 3 guys' answer together, yeah, we reach the correct answer here. Good. Very good. Very good. Okay. All good. Very good. Okay. And this is so first of all, why we need to fill up the 2 positions here? Because the number of them must be same. The number of them must be same. So you have, if you have 3 open loop poles, you must have 3 corresponding open loop zeros. One is starting point, the other is the ending point. You can't have a curve or path having starting point without ending point. And then how to fill out the rest of 2 here? We have 2 missing because we only have one finite zero, right? Only one finite zero. So how to fill the rest of 2? Infinity. I just say using infinity, because if you think that they all are the ending point of a path, then the infinity makes sense actually. It's not that scary, right? They're the ending point. We are not seeing them, but they're just out there, right? So this is how we deal with this. Good, very good. Okay. And this is the first step. The second step. Once again, we are doing nothing but following this handout. Okay, following this handout. So we're basically reached here, number 5. We reached number 5. So we're trying to plot the real axis Root Locus. To do that, what we need to do is have a axis established, real axis and imaginary axis, this as plane, and then what we do, placing all of the finite open loop zeros and open loop poles onto the plane, right? So -3, we have -2, 3, 7, and 10. So if we define, here is -1, here is 0, and then 2 is here, 3 is here, 4, 5, 6, 7, 8, 9, 10. Right? So we have open loop poles, -2, which is here. Cross, represented by cross. -7 here, cross. -10, cross. Once again, we don't have a complex open loop poles or zeros, so they're all real numbers. Nice. And don't forget open loop zeros. The open loop 0 is 93, so it's a circle. Does it make sense? So 1, 2, 3, 4. We are placing 4 spots along the real axis. As I said at the beginning today, both open loop poles and zeros count. Okay. And then we start to plot the Root Locus. So we are counting, right? Counting from the right towards left. So we first of all coming across what? -2 is 1. Right? Passing this -2 and then the left to it, we do have what? Root Locus. So we do have Root Locus between -2 and -3 because -2 here, this guy itself is 1. That's the first one. Passing -3 and then it becomes 1, 2, 2 things. 2 as even number, so left to it, and to the -7, there's nothing. Keep moving towards left. If you're coming across -7, -7 means 1, 2, 3. So this is the odd number again. So we do have Root Locus left to -7 up to the next open loop poles or zeros, right? Which is -10 here. And then passing -10, and then what do we have? 1, 2, 3, 4. 4, even number, nothing. Nothing beyond -10. Okay. Any questions? How we did this? All right, if this is fine, then we go ahead. Step into step 6. Outside the real axis. So first of all, you need to think, do we have outside real axis Root Locus? Let's come back to see. Do we have any? Anyone knows? Do we have outside Root Locus, outside real axis Root Locus? And where is it roughly? Anyone, any comments? Any thoughts? Anyone? Nothing? All right, then let's take a look at them section by section, okay? So first of all, here, this part is okay or not? Anyone out there? Is this section okay or not? Well, I don't know. It's the concentration issue, or I just don't know the answer. But anyways, this section is good, right? Why is good? Because we are seeing one starting point, which is open loop poles, and we are seeing ending point, which is open loop zeros. So you can tell the root locus for this section is from right towards left. Right? Have a direction. Remember to label the direction in the exam problem. Okay, it is required. The root locus has direction. So this section is fine, right? This section is fine. So this section, we don't need to worry about it because once again, we have one starting point, one ending point. It's complete. It's good. How about this section? How about this section? This section is same as the one we came across back in the example 4, right? Just like this. So answer is same too. So this section is definitely not right. Not okay. Since they both are poles, meaning both are starting points, and they are having root locus pointing against each other. So that's definitely going to meet somewhere in between. Meet somewhere in between, which is our breakaway point. Once again, breakaway point. Right? Breakaway point. Leaving the real axis. So the answer to this 6A is yes, we do have outside real axis locus. Yeah, we do. Okay. And therefore, we need to go ahead to find asymptote. Yep, we need asymptote. Asymptote following these two formula. One is looking for the intersection point with the real axis. Second is find the angle with the positive half real axis. Okay. So one is the intersection point for the asymptote. Second is the angle of it. Okay, two things can determine one straight line, right? Two things. One angle, one point can determine a asymptote. But once again, be careful. Asymptote is not part of the root locus. Okay, it's the asymptote, meaning asymptote. The root locus will approach into it gradually. It is not part of the root locus. Okay, so I gave you guys 2 minutes to find this asymptote and label it into your graph. Okay. All right, so 2 minutes. Go ahead. All right, anyone got the asymptote sigma sub A here? Sigma, I learned. Sigma sub A, which is the intersection point between the asymptote and the real axis. It's first of all, we can expect, we can have some expect that it's definitely between, well, it's not definitely between where, it definitely what? Real number, definitely real number. But be very careful. It's not necessarily between anywhere. Does this make sense? Well, of course, Noah got the answer of -8. Without talking about this is right or wrong, our expectation should be first of all corrected. Okay. The asymptote is not necessarily the intersection point with the real axis. Is not necessarily along the existing real axis root locus. Does this make sense? Any questions? And not necessarily at all. Okay, it's absolutely possible outside of the real axis root locus. It's outside root locus because this is asymptote. We're talking about asymptote. Asymptote gonna go through it, rather than the root locus gonna go through it. So if it end up with, for example, to here, if it's end up with -12, is it definitely wrong? No, it's not definitely wrong, right? Or -5 is definitely wrong? No, it's not definitely wrong. Does it make sense? Asymptote, okay, it's not root locus.
I got -4 and angle is pi/4, 3 pi/4, 5 pi/4, and -pi/4, and so on.
No, it's quite right. I think you made some minor mistake here. Because first of all, to correct the intersection point, sigma A is equal to -8. So Noah was correct. And the angle, correct angle is, as Alex said here, is pi/2. Okay, positive negative pi/2 or pi/2 and 3 pi/2. It's pretty much same. So, -8 and pi/2. Okay, -8 and pi/2. But anyways, the equation is what? Well, here's the formula, right? Here's the formula. So if you're writing the equation here, what should we have? Sigma A equals to what? Sigma A equals to, how about this? Denominator is 3 minus 1, right? Numerator is what? -2, -7, -10 minus -3 equals to -8. And theta A is what? Denominator remains same as 3 minus 1. Numerator is odd number of pi. Therefore, is positive negative pi/2. And take a look at this and to see any questions. Which specific number need to be explained? So here, why 3 minus 1? The reason is that here, denominator is equals to a number of finite poles minus the number of finite zeros. How many? A number means how many, right? How many finite poles? 1, 2, 3, 3 here. We have labeled the number 3 here. 1, 2, 3. That's the number. That's why it's 3. And minus the number of finite zeros. How many finite zeros? I only have 1. 3. These two are not finite zeros. They're infinite. So 3 minus 1. Right? Is it okay? Any other questions? All right, good. Now we can plot the asymptote into the picture. Asymptote, to differentiate from the root locus, I'm once again using different color and dashed line. -8 is here. -8 is here. This is the intersection point, sigma A. All right, and asymptote positive and negative I/2 is straight vertical line, right? So this is our asymptote. It's asymptote. The asymptote. All right, next, what we should do? What's the next step? Anyone knows? I'm presenting it, right? You're going to find the breakaway point. Find a breakaway point. Breakaway point, you need why breakaway point once again? You have two poles here facing each other. Breakaway point, and then this time the equation give you guys 1 minute to write yourself. Equation formula is given here. Formula is given here, and don't make the same mistake I made. Remember, here Zi and Pi are negative open loop zeros and poles. Okay, go ahead. If you're able to, then feel free to calculate the value as well. Yep, I'm seeing correct answer from both Kevin and Sawyer. So we can see the equation here. So the equation is actually like this, right? This equation is, once again, we have a bunch of reciprocal. So here is sigma minus 2, sigma minus 7, sigma minus 10 equals to 1 over sigma minus 3 plus 0 plus 0. Does it make sense? Because these two zeros representing 1 over what? Infinity, right? 1 over infinity. So from this equation, you're able to find the sigma, which is equal to negative 8.47. So as we had back in the previous example, this number is right between these two poles, right? Right between the two poles. Perfect sense. This sigma is the breakaway point. Obviously, it must be between, or say along the real axis, root locus. Okay. So negative 8. This is negative 8. This is negative 9. So basically, between right in the between negative 9 and negative 8, right? Right between here. This is a breakaway point. Breakaway point after leaving the real axis is what? Approaching to the asymptote. This is how we use the asymptote. Okay. After finding the asymptote, we are not using it yet until we find the breakaway point. Because after leaving the breakaway point, the root locus is trying to approaching to this asymptote. Okay, trying to approaching to it. So actually, what does it look like? It roughly looks like this. Okay, it roughly looks like this. Remember, label the direction. Once again, I'm using the dark black to represent the Root Locus. Okay. Different color. Hopefully you can differentiate it with other. This is how we use this asymptote. Okay. It's really approaching to it. And that, since we have no complex open loop poles or zeros, so we're done here. Okay. This is the Root Locus sketched. Any questions how to plot the Root Locus by hand? Any questions?
If we say that k is a positive 1, then that gives us 3/2 pi, right? Why?
Hold on. You mean n here, right? Or any constant value? You mean here, right?
Yeah. Why
Okay,
is it that we don't have that?
If you're saying if this value is equal to what? Once again, 1, right?
Yeah.
Then theta A equals to what? Pi, right? Right? No, this is what? Pi over 3. Pi 3 pi over 2, right? Pi 3 pi over 2. 3 pi over 2 is what? Where is it? 3 pi over 2.
70.
70.
270 degrees.
270, correct. Okay, 270
Huh.
is what?
Yeah.
Does it make sense? So this asymptote is 2 asymptote. Your understanding of this asymptote should be 2. This is 1. This is another one. Right? This one has 90 degree. This one has what? 390 degree, right? That's right. Okay, Sawyer was right. Okay, it's the line down. That's the second asymptote. Because remember, the Root Locus is symmetrical about the real axis. So does the asymptote. Right? Perfect sense. Right? So does the asymptote. Right? Any other questions regarding this?
I think you got the number mixed up on breakaway points. Should the number be positive, not negative?
Breakaway point, you mean this one?
No, like 1/sigma - 2. Should that be positive and the rest of it?
Oh yeah, this is a positive 2, right? Although that's right. This is positive. That's right. I'm sorry. It's positive. Correct. Thank you, too. Thank you. Supposed to be positive. That's right. Yes. Sigma plus the negative of -2. That means sigma plus 2. That's right. Yeah, that's right. Thank you. Any other questions? All right, if this is fine, then we can go ahead and start the next module. Module 7, the design via Root Locus. This design means, of course, design control. And in our mind, we are talking about a system like this. This is something we have talked about in the past. right? Originally, we have a system with transfer function P and with feedback transfer function of H. Is already a closed loop system. And we are now designing a controller right before the P, and also involved in the forward path. I mean, not here, okay, not here, not here either. It's right before the P. Okay, not here, not here. Okay, this is the system block diagram, visualized one in your mind. First, we need to understand the controller design objectives. What objectives we are targeting? We are trying to achieve. Remain at those three things. Okay. The first priority is what? Stability, right? So your controller, after designing this controller, you need to keep, if not improve, the stability. So it must be stable. Okay? My system must be stable. Otherwise, nothing is meaningful. If it is, then go ahead. What's the next? Anyone remember? Based on what we have learned in the past, what's the next objective?
The error.
Error. Okay, very good. It's the error, or say the steady state error of output. What do you want? Of course, it's optimal, and we don't want any steady state error. Okay, no steady state error, no steady state error, okay, no steady state error. And here, actually, we can only specify in one particular input, right? Because steady state error is what? Input dependent. Remember that? It's input dependent. You have different inputs, your steady state error is going to be different. So here we just focus on what? Step input. We're trying to make the step input steady state error vanish. If so, then the last concern is what? The last concern is what?
Transient.
Transit, very good. Molly is correct. Okay, so we're trying to so-called a decent transit. Very good, decent transit. Okay. And here, of course, including bunch of specifications. We're trying to improve. So the controller design objective. There's nothing else we do, not this, and at least not this course. Okay. And then next, the design methods. We actually have two methods, and one is Root Locus, which we're gonna study in this module. We have also another so-called frequency domain method. Of course, in the Root Locus here, we are also using the frequency domain transfer function. In terms of what? S, right? But that's not the frequency domain design method we refer to. The ones we refer to here is actually the Bodie plot, the Bodie plots. Okay, you guys probably learned that, or say at least use that in 358 or any other electronic circuit. You're looking for the frequency response. 318 probably you did a little bit without being aware of it. In 358 is quite a bit a subject you need to understand. Okay, the Bodie plot and the Nyquist plot. Nyquist. So because of the time limit, this course gonna teach this one. I'm gonna teach this one. Teach this one. Leave the Nyquist into advanced control class. This is design. Of course, this module is about here. Yeah, so this module is about this Root Locus. And we want to specify a controller. What controller we are learning from this course? Okay, just a very basic one. The controller here means what? Just a PID. How to design a PID controller. Okay. By the way, PID is equals to what? PID controller is mathematically equals to this, right? P is standing for what? What is it? Anyone knows? P is what? Proportional, correct. P is proportional. Proportional, of course, is individual gain here. I is what? Integral. It's the integral. Here we go. The integral is this guy. D is what? Is this guy. What is it? Derivative. Oh, by the way, this is the integral. This is the derivative. Why? Anyone knows why? How we know that?
But that itself is like the Laplace, right?
Exactly. Very good. Is this clear? Integral itself with respect to t, okay. Laplace is equal to 1 over s. Derivative something with respect to the time t is Laplace result is s. There's no function here and here. Okay, no, nothing. Just the operator itself as a Laplace transfer function in frequency domain. Okay, that's why this is integral. This is a derivative. Okay. Any questions? All right, then let's see this. So this guy further can be organized into such format, right? Now from here, actually, you can tell the PID is actually introducing what to the system? It's introducing one zero pole, right? 1 0 pole. That makes sense. This S in the denominator means nothing but 0 pole. And also introducing what? This means what? Anyone? This means anything to you? The numerator?
2 zeros.
Zeros. How many zeros?
2.
2 zeros. Okay. 2 zeros. Here, don't take me wrong, this is 1 0 pole, or say 1 pole with value of 0. This is what does this mean? 2 zeros means number is 2. What are the values? Well, it's up to the roots of the polynomial. Right? What else this means to you? Also very important. Anyone can tell? Here, introducing 1 0 pole. Here, you can tell, introducing 2 zeros. And what? Anyone tell? And also introducing what? Very, very important. What is it? Very good. Excellent. Kevin's right. Never forget. It's very important. Okay. It's also introducing different games. Okay. It's absolutely important. You see. Okay. You see that. Very good. Very good. This is nothing but introducing a new game. Okay. It matters a lot. Okay. Good. Very good. This is a control. We just study the PID. Okay. And see the nature about this. Okay. Nature about this. To study the PID, we can begin with the very easy one, the most basic one, which is to study the P controller itself. P controller. In other words, we only have a gain, constant gain KP. We give this to the system, right? We give this to the system, which means we have a KP, right? So a new gain to the original system. Let's see what this guy can do, especially to the Root Locus. Right? How the Root Locus is going to change? After introducing this KP, how the Root Locus is going to change? Anyone knows?
Well, the plant. Oh, the root locus. Never mind.
All right. Anyone knows how the Root? Here, Sawyer is saying KP is just a gain, so it won't change, right? Yes. Okay. No change of the original Root Locus. Okay. No change. Now, of course, after introducing the KP, it's something different, right? Then what is the difference? The system becomes different, obviously different, because you're introducing new gain here. And what's the difference? How about this? Okay, this is probably a little bit hard to understand, but assuming we have original Root Locus like this. I'm just copying the example 4 we just studied. Locus is like this, right? So basically, looks like this. This is the original system. Original system Root Locus like this. Now I give a KP here. I gave a KP here. And how the Root Locus is going to change? No change. Then what's the difference then? Well, Kevin's saying, well, increase the open loop transfer function by factor of KP. So, very good. Sawyer is right again. Okay, it's changing the pole locations. Excellent answer. Okay, excellent answer. Everybody listen up. This is a very important understanding. Okay. Root Locus is a path. Along the path are infinity number of poles locations, right? With different K values. So if without this KP, the original system, P and H, this system, the poles are fixed at one point. Because here it is a specific system. The poles, closed loop poles are one fixed point. Itself is not path. So somewhere, maybe that pole might be here, might be here. It might be here. Obviously, 3 poles. Right? This is the original. Here, I'll give you a legend. This is original closed loop poles. Okay. After giving a KP, what happened? Your closed loop pole location moves. Does it make sense? It really moves. Moves to maybe somewhere here. after introducing KP. Closed loop. Okay, very good, very good. Okay, Sawyer's understanding is good. Okay, it's good. After introducing the KP, gain itself, and what happened? Root locus, the look is there's no change there. Okay, there's no change there. The only difference is you have new system. New system closed loop post location is different. One specific system has, of course, specific point along the root locus. Here, okay, I was asking is so it hits the next point on the root locus at a lower k value when plotting k equals 0 to infinity. Lower k value when plotting k to infinity. I'm not quite follow this question. What does this mean? His next point on obviously, this KP, generally speaking, is greater than 1, right? Greater than 1 then means what? Your gain, K there, is increasing. So that's why it's moving down along the given root locus direction. That is from original red towards the blue. I mean, if original is at red, then given the KP generally speaking is greater than 1. Let's or say if we assume KP is greater than 1, then the result is new blue color closed loop pole location can move down to along the root locus, right? Move down means from red to blue, rather than moving the other way around here. Only move down because we have direction, remember? Move down along the direction. But KP, if KP is less than 1, what happened? The other way around, moving here. Does it make some sense?
So if our system actually had like a KP, it could potentially, if it's too high, become an unstable system then, right?
Absolutely. Absolutely. That's the next thing I wanna mention. Can change what? Stability. Very good point. Very good point. Because if you gave KP too high, you might achieve better specification in, the transit. That's possible. However, you're at risk of losing the stability, okay? Because it might be beyond the y-axis and becomes unstable. Right. This is the what P can do. So it won't change the original root locus, but it will move your closed loop poles along the root locus. Location is different, okay, because your poles are different. Very simple, because generally speaking, we won't use the P itself alone, right? So we generally speaking use what? Who is the most popular controller, actually? And this is very common sense. Excuse me, right? So who is the most popular controller? Not P, right? What is it? PI, right? PI is the most commonly used controller. PI. It is KP plus another integral term. If you organize in such a way that you can tell immediately what PI is introducing, right? So from here, what is introducing? 1, 0 pole. And here is what? 1, 0. And what? New gain. You see, it is doing more than P itself. Right? It's doing more than P itself. Right? So what can this do? What can this do? PI has 1, 0 pole added to the system. Is there anyone remember a 0 pole, or say the order of 0 pole in the system transfer function, forward transfer function, means what? What is the definition, or say what is the name we ever had for it?
Well, 0 is the spot that it will end at.
The
Or-
states, no, it's not that one. When we study the steady state error, that module, system type. Here we go. Jeff is right. Very good. Jeff got it. Jeff got it. System type increased by 1, right? Because you are adding 1 0 pole here. The system type increased by 1. Which means what? New system type is what? New system type is at least 1. Does this make some sense? Okay. And further, the system type at least 1. What is the conclusion here? How about the steady state error? Anyone remember any conclusion here? How is it? To particularly step input. What is it? Any memory? Well, yep, 2 is right. It's 0, right? Guess what? This is exactly what we want. It's what we want. Okay. It's because once again, going back to here, the design objectives, right? The design objective. What do you want? So as long as you, which means what? Which means as long as you are using PI controller without even thinking of the KP, KI values, as long as you're using PI controller, what happened? It guarantee a 0 step steady state error. Okay, it's guaranteed 0 steady state error. Guarantee you. It's the first thing you need to keep in mind. It's guaranteed that. And you can later on you can play with the 0 location here and value here to improve the Root Locus, therefore further improve the transient. Any questions? All right, if nothing for today, and then just you guys have a good weekend. We can stop here. And by next Monday, we will have well, first I received a super long question here, and maybe
So pretty much, I just wanted to go back to that. When we do just the P, all we're effectively doing is just adding an additional gain to the system, correct? Because back when we started this, the root locus was just the points of the closed loop transfer function poles as we varied K from 0 to infinity. So when we apply the KP, it's just like putting a new gain on there. So when we hit K1 at a value of K equals 100, now we might hit it at like 5 or 10 or something.
yes, that's right.
Okay.
Because you are talking about it at same location, right?
Correct. Same location.
Yes, same location. However, here I'm talking about your post location. Your post location is
Moving
is
out.
moved. Yep. But if you're pointing to somewhere like the same location, to two different, the new original root locus and the new root locus, same location here and here, same location.
K value will be
You're gonna
low.
have exactly different K values.
That's what I wanted to make sure.
All right. Yeah, you can also see how efficient it becomes after turning typing into a conversation orally, right? So, yeah, speak out. Okay, speak out, everybody.
Definitely. I just wanted to type it so I didn't forget.
Okay. All right. So once again, you guys have a good weekend, and talk to you guys next Monday. All right. Bye-bye.